Dat snap ik wel, dat is niet helemaal maximus strak. Hij heeft gewoon die ruimte.
Ja, het is super subjectief. Ik heb natuurlijk een hele oranje oog, dus ik zie het helemaal maximus.
Okay, let's slowly get started. How was the first week? Any comments? Any ideas? Scared? There's no need for that. Yeah, we're at a very slow pace. We're going to cover all the topics that were treated on last Friday. So basically, the regression framework up until a GLM, and that includes simple T-Test and chi-square test. And then we're going to expand it so we can do more groups, we can do combinations of continuous and categorical variables, and we're just going to expand it more and more and more so that this regression thing becomes a more and more useful tool that you can apply to a very wide range of problems. So the topic of today is the T-Test. I will also quickly show you the third year course. Yeah, so in the third year course we have chapter 5. That's about statistical tests, and that's where the assignments are. So there's also the 2 videos, which is what I'm going to talk about now, and in between the videos there's assignments. So this one you have to choose a test, and this one is about interpreting output. Interpreting output will definitely be on the exam, so do have a look at these exercises because it's very much like the exam. There's also a new exercise, number 7, which is just like on Friday. It's a PDF you can download. There's an R Markdown file and an R data file. If you download those 2, I will show it at the end again. Then you can have a look at this. These are more challenging problems. We will discuss these tomorrow morning. If you get these wrong, that doesn't really say anything about your passing of this course. The ones you should get right are the ones over here. So yeah, these and these. Yeah, but wherever it says hard, it's just for people who are done with this quickly or like, well, I already know what a t-test is. So you have something interesting. But for everyone else, just go through the exercises that don't say hard, and if you fail the ones that say hard, that doesn't mean anything. Okay, make this a little bit bigger, and then we can talk about the t-test. Okay, I am watching the... Okay, my phone doesn't agree. Yeah, sorry. I am watching the chat from my phone, so if anyone is listening at home or somewhere else, and there's a problem with the video or the audio, just type something and I will try to fix it. Okay, so t-test, I'm going to talk about it in 2 different parts. First one, I'm just going to give an overview of the different types of t-tests there are and why you would use the different types and why the default is the default, how you can do it in R, and how you can interpret the output. And in the second one, I'm going to explain what's actually going on and why is this the way that we compare to group means. So a t-test is, I think, the simplest test that there is. It's also a test that is very, very frequently used, and it will keep returning throughout the course. It's very useful. It's basically a comparison of 2 group means. Yeah, so you start by taking on a null hypothesis that there is no means. No difference in means, and then you're going to build evidence against this null hypothesis through your sample, and the stronger your evidence, the less likely this null hypothesis is to be true, and then at some point your evidence is so strong that you reject the null hypothesis in favor of the alternative, that apparently there is a difference. And when that's the case, you call the difference significant. Now, how large your value t should be, or how large your evidence against the null hypothesis should be in order to reject it, that depends on what you consider to be the acceptable chance of a false positive. Yeah, so maybe in a bachelor course you might have heard something like, yeah, if p is lower than 0.05, it's significant. That's a bit of an oversimplification. It's significant when it's lower than the level that you chose. And it just so happens to be that 0.05 is a popular level, but there's no reason you couldn't choose another level. So, for example, let's say that you're conducting a test to decide who should receive a certain type of treatment, like chemotherapy. You don't want to treat people who don't have cancer with chemotherapy because it's very taxing. So you would choose a much, much stricter level. Yeah, of course you wouldn't use a test for that in the first place, but the more real example is in elementary physics, particle physics. They use a level called 5 sigma, well, sigma is the standard deviation. That means you want to be 5 standard deviations away from 0 before you conclude something as significant. And that would be equal to an alpha level of 0.000, a whole bunch of zeros, and then a 1. The point being, you can choose different levels. Yeah, and if you have a very small sample size, just a pilot study, you know, error is not a big deal. You can be more loose with it. You can choose 0.1, for example. Okay, so the simplest version of a t-test is called the one-sample t-test. And it's called one-sample t-test because there's only one sample. What you essentially want to do in a one-sample t-test is you want to compare the group mean to a theoretical value. So let's say I want to know whether men deviate, you know, adult males in the Netherlands, whether they deviate from an average height of 1.8 meters. You could do that with one sample t-test. Yeah, I could measure the height of the people in this room, and I could, you know, calculate the average, and then see that it, you know, it probably deviates from 1.8, but I don't know by how much, and I don't know how much people differ from each other. So that's why we're going to do a test. Yeah, because it's just a sample. It's just one of many possible draws. So just because it differs doesn't mean that it's a significant difference, and that's what we're going to find out with a test. So in this example, we have 6 males with an average height of 1.85, but again, every individual is different. Some are lower than 1.8, some are higher. So is this or is this not a significant difference from 1.8? Now, we need a little bit more information than just the mean to answer that question. In R, it's very simple. You know, just put these numbers into a vector, like I've done over here. So C means concatenate, so bind them together. So now we have a vector height that contains 6 values. Just say t.test height. That will perform the t-test. And I want to specify that the value under the null hypothesis, the theoretical value, is 1.8 meters. Now, how large is our evidence against this null hypothesis? That's a bit tricky to express. We use a p-value, which is a very tricky meaning. It means that if, on average, males have a height of 1.8 meters, so if the null hypothesis is actually true, then there is a 17.4% chance that you would draw a sample with this large a deviation. Yeah, so then the answer is okay. Is that significant? Depends on whether your level alpha is greater or less than this 17.4%. So if we choose the commonly used level of 0.05, then we would say, well, okay, if the null hypothesis were true, there's still 17.4% chance, which is much higher than our accepted false positive rate. So this difference, we don't call it significant. Yeah? And another way to interpret a negative result like this is to say these males may as well have come from a population with a height of 1.8 meters. We have insufficient evidence to conclude otherwise. Okay, you can also ask other questions with one sample t-test. Here I just asked, is it different, right? But maybe I want to know, are males in the Netherlands taller than 1.8 meters? You can do that simply by specifying alternative is greater. Yeah, and then it will ask, is the mean of this vector significantly greater than the mean under the null hypothesis? And you can do it the other way around. You can say less, and then it will perform a one-sided t-test instead of a two-sided t-test. Now, the p-value is half when you do this. So it will be much more significant if you do this in the right direction. But of course, you can only choose to do this before you see the results of your experiment, because otherwise it's cheating. You're not really asking for the difference in one direction, but first you're looking, and then you're concluding you should look in that direction. That's called p-hacking, so that's something to avoid. Okay, next is the two-sample t-test. In this case, you compare two groups. So we have a group of men, which have an average height of 1.85, and a group of women, which have an average height of 1.72. But again, we're not interested in these individuals. We're interested in the source of these individuals, right? So do these groups differ significantly, or could they have come from a population where males and females have equal height? That's what we want to find out. So in R again, very simple, just enter both of them as a string of numbers. So here we have a vector for male height, I called it height m, and here we have it for the female height. And it's stupidly simple, just t.test the first group, comma, the second group, and that will give you the result. There is also another way to enter t-test in R, as you may have seen in the assignment last week, which is the formula notation, but we will get back to that during the regression lecture. Now, in this case, we see a bunch of outputs. For now, we're just going to restrict ourselves to the p-value. I'll explain the rest in the second half. In this case, the p-value is quite low. It's 0.008962. Now, again, if we would choose an acceptable false positive level of 0.05, then we would conclude that there is a significant difference in height, because the chance, if males and females did actually have equal height on average in the population, then there's only a 0.9% chance that you would draw a sample with this large a difference. And that, that percentage is much lower than the agreed upon 5%. So you say, okay, the null hypothesis is probably not true. So we reject it, and we have sufficient evidence. Yeah? And again, just like with the one sample t-test, also with the two sample t-test, you can test in both directions, or in one direction, or in the other direction. So the default is to test two-sided. Yeah, so that's just asking the question, is there a difference? And you are naive to whether it's a positive or a negative difference. But if you want to know, are men taller than women, you can also ask that question, and it'll give you a different p-value, because you're only assessing one side of the t-distribution. And in that case, just specify alternative is greater. And if you can do greater, you can do less. So there's also the other alternative. Yeah, and again, you have to choose this before seeing your results. Okay, this is too large. Yeah. Okay, then there are a couple of choices that you have to make when you conduct a two-sample t-test. The default is to do unequal variance and two-sample t-test. I will explain later why that is the default, but let me first explain what it even means, whether to assume equal variance or not. Variance is the extent to which individuals differ. So what you're really saying with an equal variance t-test is you're saying that though these groups may differ on average, the extent to which individuals in the group differ from each other is more or less the same. That's what you do with equal variance. That's the top picture over here. In the bottom picture, that's what it would look like if variance were not equal. So there's still a difference in mean. Men on average 1.8, women on average 1.7. But in this case, the variance of women is much larger than the variance of men. Yeah, so that is how you should visualize, try to visualize what it would be like if the variance were equal or unequal, and then decide for yourself. In this context, for height, I don't have any reason to assume that women differ to another extent than men, so I would assume equal variance, and that gives you a more powerful test. Okay, that's just another argument. So you do the same test, t.test, height m, height f, and that will compare the mean of males to that of females. But I'm going to specify an extra argument as var.equal. If I set it to true, it will give me a slightly more powerful test if the variance is indeed more or less equal. But sometimes you don't know. Sometimes you have values for which it's just really hard to guess, is variance going to be equal, yes or no? I have no idea. In that case, it is much safer to just specify false, var equal false, which is the default. That will give you slightly less power, and power is your ability to demonstrate a significant effect with your sample if there is a real difference in the population. So that power will be slightly reduced with unequal variance, but it's a safer assumption. So the p-value is correct even when variances are unequal, but also when they are equal. So this test is always correct to do in terms of false positives. This test is only correct if variances are indeed equal. Okay, there's another choice to be made, which is whether your data are independent or paired. So independent or dependent. Now, independent data means that every observation that you have is distinct from the others. So in the case of men and women, well, we had 10 individuals, and we didn't measure them multiple times or anything. So these are individual experimental units. Yeah, but if I have another experiment, like the sleep data from last week, or let's say we have some blood pressure reducing drug, then first I measure hypertension patients, their blood pressure, then I give them a blood pressure reducing drug, then I measure again. It makes sense, right? This kind of study design. But it would yield you dependent data because it's the same individuals. So really you don't have, in this case, let's see, what is this, 12? 12. So you don't have 12 observations, but actually you only have 6 because there's 6 individuals, you just measured them twice. If that's the case, you need a paired t-test. Now, how to do a paired t-test is not much different. Here I've recreated the data from the figure that I just showed. So here we have the before data, and here we have the after data. When you do this, it's important that they actually correspond, right? So the first one, 127, this must be the same individual as this. Yeah, and this must be the same individual as that, because that is what paired means. Then I say, is there a difference before and after using a medicine? The only thing I have to do now is, again, t.test vector 1, vector 2, but now I specify paired is true. Now, if you do that, it will perform a different kind of test, which has a correct p-value. Everything that we discussed so far, so testing in one direction or in two directions, you can also do it with a paired t-test. So just, add arguments, add another comma and say alternative is greater. Yeah, and then I'm asking, are the before measurements on average greater than the after measurements? Yeah, which is actually asking the question, is this blood pressure drug working? Right, because we want to lower blood pressure in hypertension patients. You can also specify a value under the null hypothesis. So I might ask the question, is it significantly different from 5 millimeters of mercury, the decrease? Or I can even ask both at the same time. I can do one-sided paired t-test. Has it fallen more than 5 millimeters of mercury? Maybe if it has fallen less than that, it's not enough of a medicine. Maybe I want something that does at least that. Then you can ask questions like this. Okay, so that's the one sample, two sample t-test. Now, these are not t-tests, these are alternatives to the t-test when the t-test is not valid. So, something I didn't talk about yet is the underlying assumption of the t-test. So it assumes that the values within the groups are normally distributed. This is what a normal distribution looks like. So you have a mean, and further values are exponentially less likely. It's symmetric, it's continuous, goes all the way from minus to plus infinity. The question is not, is this true? Because of course height does not range from minus to plus infinity. The question is this a reasonable approximation? And I think for height this is a reasonable approximation. In the second lecture I will come back as to why I think it's a reasonable approximation. But let's just take another moment to see what exactly it means when you assume this. So in this case we have a mean of 1.8 and a standard deviation of 0.07, so 7 centimeters. That means that I expect 68% of males to be within 1 standard deviation and 95% to be within about 2 standard deviations. So you can calculate, okay, where do I expect what proportion of the population to be? Yeah, and then you're also saying that further deviations are exceedingly more rare. So if you are an adult male in the Netherlands and your height is less than 166 or more than 194, that should be the exception and not the rule. Okay, let me take a question to let me take some moment to read the questions. What happens with the alpha value when testing one-sided? Okay, it's independent. Alpha is chosen before you see any data. So you choose alpha as the level that you tolerate false positives. It has nothing to do with testing one or two-sided. Can you explain 8.0 again? When can you say it is significant and when not? Okay, so you start by assuming there is no difference. That's the null hypothesis. And then you're going to see if the null hypothesis is true, how likely is it to draw a sample with this large deviation? If that chance is very low, so if the deviation is very large, then you reject the null hypothesis. The way to see that is that the p-value is very small, because p is the chance of drawing that large a difference from 0 if the actual difference is 0. Why guessing if variance is equal when you have the data you could calculate the variance? Yeah, it's a good question. It's an ongoing discussion among statisticians. You could perform some tests, like is the variance equal or not, but yeah, there's some problems with that, because that test also has a chance of a false positive. So you're using the same data twice to decide which p-value to look at, which in general is something frowned upon because it increases the overall chance of a false positive. So I would just reason, and if you can't think of a good reason that the variances should be approximately equal, go with the unequal variance t-test, which is a safer assumption. Okay, then, so this was the normal distribution, yeah? But there are a lot of types of data that you cannot assume are approximately normal. Adult male height in the Netherlands, sure, approximately normal. But if I count the number of birds in the park, I cannot count 0.1 birds or -1 bird or -2 birds. So this distribution is very peculiar. It only takes on certain values and only non-negative integer values. That's called a Poisson distribution. If the mean is close to 0, then what happens is because the values cannot be negative, the distribution gets pressed up into the side, into the axis. You also see it over here, which means that the right tail of the distribution is much longer than the left tail. And that means the distribution is asymmetric, and it also means that the mean usually is not at the top of this distribution. So then the question is, does it still make sense to compare means? Because you're not comparing the most common value. Okay, then we have another example, which is a binomial distribution. So this is number of correct questions out of, number correct out of 20 questions. You can have 0 questions right, you can have all of the questions right, but you cannot answer more questions right than there are, and you cannot answer less than 0 questions right. So this has the same problem as with the Poisson distribution, except in 2 directions, where if it gets close to the side, so close to 20, close to 0, it's going to be asymmetric. It's also, of course, a discrete probability distribution, it's usually not well approximated by a normal distribution, unless there would be a very large number of questions, and most people are somewhere, in the middle, like most people answer about 50% right. In that case, it would look more or less normal. In any other case, it's better to use something else. Now, last example, this is a continuous distribution. This is the exponential distribution, it's very asymmetric. And can anyone guess where the mean of this distribution is? I don't know if the numbers are readable. This is 0, 1, 2, 3, 4. Where do you think the mean is?
1, 2.
At 2. Anyone else? Yeah, I made this one with a mean of 1. So the point being, if you're going to compare groups that look like this, then what is the point of comparing means, right? What is the special meaning of this value over here? So in that case, it's better to use a different type of test. We have those tests, and they work exactly the same as a t-test in R, except that you have to specify that you want to perform a Wilcoxon test instead of a t-test. Yeah, and all the options I just discussed, like testing one-sided, doing a one-sample t-test, doing a paired t-test, is all possible for the Wilcoxon test as well, with one exception, which is equal variance. There is no assumption of what distribution the data follows, and because of that, there's also no assumption about the variance of that distribution. So there is no var.equal argument. But all the other options we discussed, you can do with a Wilcoxon test in exactly the same way that you would with a t-test. Okay, now I'm going to give a quick summary, and then I'm going to take a short break, and then I'll explain how the t-test works. So these are the options we discussed and how they look like in R. So we had the default, which is a two-sample, two-sided t-test for unequal variance. Why is this the default? Because it's the safest of the assumptions you can make. If you have no specific reason to assume one group to be larger than the other, then you'll get a more fair p-value to just do a two-sided t-test. And if you don't know that the variances should be equal within groups, then it's safer to assume that they're not. So that's the default. You can test one-sided if you have a reason to, which is by specifying the alternative. Yeah, and the alternative means if the null hypothesis says that there's no difference, the alternative is what happens if you reject the null hypothesis. So in this case, your presumption is that the mean of this group is greater than the mean of this group. You can assume equal variance with the var.equal argument. You can do one sample t-test, then you only have one vector, but you should specify what the value under the null hypothesis is. If you don't, it will compare it to 0. Yeah, so that has also an important reason, but we're not going to see that until we get to linear regression. Finally, we have a paired t-test, which you just do by specifying paired equals true. Now, you can mix and combine these arguments as you see fit, depending on what you think is the appropriate t-test to conduct. So yeah, they're not really difficult assumptions, and you know, if you're not sure about them, there's always a safer version of the other. But you should think about this because, of course, you want the most powerful test to get the most out of your data. Now, finally, if normality is not a reasonable assumption, you can use the Wilcoxon test instead of the t-test. Okay, let's get to the output. So far we only looked at the p-value, but there's a lot more going on here. So let's have a look at everything over here and what it means. Well, it starts by stating which test is performed. In this case, I specified var.equals true, which performs an equal variance t-test. And it's just called the two-sample t-test. Then it says what the input is. So the data is height m, which is the first vector, and height f, which is the second vector. And then it says the t-value. Now this t-value, all the way at the beginning of the lecture, I showed it briefly. I will show it again in the second lecture. It's just the difference in means divided by the standard error. And the larger this value, the greater our evidence against the null hypothesis. Now, what this value should be exactly, it depends on how many samples you have, and it depends on your accepted level of false positive, so alpha. Now, then we have the degrees of freedom, 10. So that means that there were how many observations here?
12.
Yes, and why?
And I don't know.
Yeah, because you calculated two means, so you use 2 degrees of freedom. And if there's 10 degrees of freedom left, then you have 10 plus 2 equals 12 samples. And we have a p-value, which using these two values, I will not show it here, I'll show it in the next half. You can compute this value, which is the chance that if the null hypothesis is true, that you would still see this large a difference. Now, also in this example, that chance is really small, so then we would reject the null hypothesis in favor of the alternative, which is specified here, that the true difference in means is not equal to 0. Then we get to a confidence interval. This is always nice because, of course, you can calculate what the actual difference is. In this case, it's 14 centimeters or something. But there's uncertainty, right? Not everyone is the same. There are, in fact, women who are taller than men. So, yeah, you want a range within which you think this difference is. And the confidence interval gives you something like that. So in this case, it says that there is a difference between 4 and 23 centimeters. Yeah? And that's much more informative than just this one value, because not only is the actual difference is inside this confidence interval, but also it gives you an idea of, okay, I'm not quite sure what the difference is, but it should be between these values. Now, then finally it just reiterates the computed means with which it performed the test. So it says the first group has a mean of 1.8, second group has a mean of 1.7. This is occasionally useful when you're not quite sure you used the t-test correctly and you want to know, okay, should I do alternative greater or less? Greater means that this one should be bigger than this one, and less means that this one should be smaller than this one. So that's an easy way to see, okay, which one did I have in mind? Yeah, that's everything in the simple output. Now, over here, I'm still doing a equal variance t-test. There's a reason for that. I'll show the other one in the second half. But now I specify alternative is greater. What does that do again?
Creates a one-sided t-test.
Yeah, exactly. When you specify the alternative, then I'm only interested in is the mean of this group greater than the mean in this group. And in that case, there's only one side of the t-distribution we look at, so it's a one-sided t-test. It will give you a different p-value. That's one thing. You'll only notice it if you perform both t-tests, of course, but yeah, you'll have to take my word for it. But something else happens, namely the 95% confidence interval now ranges from 6 centimeters all the way to infinity. So does anyone have an idea why this is happening? Yes?
Because we're looking just at one side, so the other side says infinity, but it doesn't really mean much here because we're not looking at the data in that direction.
Yeah, exactly. It is because of this test being one-sided. We're only interested in one difference, so this doesn't mean that we actually think the difference is infinite. It just means it is at least 6 centimeters, and it can be any value greater because we didn't look at the other side. We didn't estimate that. Yeah? So it just means it's larger than 6 centimeters, or in other words, it is at least 6 centimeters. Okay, that's all for the first lecture. So let's have a 10-minute break, and then we'll get to how it works. Oh, are there any questions? Yes?
In the paper, do you mention the confidence interval?
Okay, yeah, a very good question. Let me quickly cover that before we go to the break. We have 1 minute left. In a paper, do you mention the confidence interval? Yes, I would definitely mention the confidence interval because it is more informative than the actual difference you observed. And in fact, there are a lot of people who think that reporting a confidence interval is also better than reporting the p-value, but that's a discussion for another day. Okay, then we'll continue at 9:55. Okay, let's slowly get started again. There was a question during the break. What is the null hypothesis when you specify alternative is greater? This would be the pair of null and alternative hypothesis. So the null hypothesis H0 is that the mean is less than or equal to 0. For if that is not true, then the alternative must be that it's greater. Yeah? And the other way around, when you say alternative is less, then it would be like this and like this. Yeah, so this would be, alternative is less. Yeah, so it's everything that is not less would be the null. Are there other questions? There was another question in the break, whether you can just test whether your data is normally distributed. That's actually a good question. It's a bit of a problem. Of course, you can test for deviations from normality with a Shapiro-Wilks test, but if that test is significant, it means that your data deviates significantly from a theoretical normal distribution with its own 5% chance of having a false positive. And if that test is not significant, it doesn't mean your data are normally distributed. It just means there is no significant difference from a theoretical normal distribution. But that doesn't in any way prove that your data is normally distributed. So it's better to just think about it. And if you know your data ratios, yes, there are certain specific circumstances where a t-test is still valid for a ratio. But we're going to learn about GLMs in this course, so there's no reason to do a t-test in that case. You can do something more appropriate, which will also give you a more interesting answer to your question. If you do want to, if you have a scenario where you think your variable might be normally distributed, you're not quite sure how to proceed. I did write about this in the first book. So this is Introduction to Biostatistics, paragraph 6.3, where I talk about how you could assess it. So these are 6 draws from an actual theoretical normal distribution, and in my opinion, they don't look particularly normal. It's just because they're small samples, right? But almost all research, in biology at least, concerns small samples. So it is really hard to tell whether something is or isn't normally distributed through some test, and even through a QQ plot, which is a much better way to do it. You should really think about it, whether it makes sense from a theoretical point of view, but I will come back to that at the end of this second lecture, how you can substantiate from a theoretical point of view whether your data should or should not be approximately normal. Okay, any other questions? If not, then we can continue. Okay, so we quickly covered how you can do the test in R and what the different choices are. Now I'm going to go a bit more in depth into how the t-test works and why it works this way, and also what it actually looks like when you choose those different arguments. Okay, so this is what the actual one sample t-test looks like. You have a sample mean, which we call y bar. Bar just means something is averaged. Y is your value of interest, so maybe human height or something. And we compare it to a value under the null hypothesis. So the mean, mu, 0 for being under the null hypothesis, which is the value we choose. And we divide it by the standard error. So the only real question is how to calculate the standard error, because this one we choose. This one is very easy to calculate, it's just the mean. So this is the only one you have to learn. Now, what just happened? Okay. And then it jumped a great number of slides. So let's go back to where we were. Yeah, sorry, we're back where we were. So this mu 0 can be whatever you want. If you don't specify anything, it will compare it to 0, which is interesting, for example, in linear regression, where you want to know, is there a significant relationship, which is the same as asking, is the slope significantly non-zero? So that's actually one sample t-test. But, in the case of our male students significantly taller than 1.8, then mu 0 is 1.8. And if you want to know, does the average body temperature in this class differ significantly from 37 degrees Celsius, then mu 0 is 37. So it's a choice. It's whatever you want it to be. Okay, so what you do is you create a set of hypotheses. So actually I have the null hypothesis here. So this is what the null and alternative hypothesis look like when you perform a one sample, one-sided t-test. Because you want to know, is the mean greater than 1.8, then the null hypothesis is the opposite of that, which must include all other options. So that is it any value equal to or less than 1.8 meters? Now, what we're going to do is we're going to calculate this t value. So first we calculate the mean, which we already saw in the previous lecture, which happened to be about 1.85. We subtract the mean under the null hypothesis. So, okay, there is a difference of 5 centimeters, but we don't know if it's significant. And then the only thing we have to do is divide it by the standard error to get a t value. Now, the standard error is a measure of uncertainty. So the greater the standard error, the less certain we are, the weaker our evidence. And the smaller the standard error, the more precise this difference is, and the more certain we are that there is a real difference. Now, what is the standard error comprised of? The standard deviation and the sample size. That should make sense intuitively, because if individuals differ a lot from each other, then there is more uncertainty. And if everyone is more or less the same, then you're very certain about your results. And if you have a very small sample, then yeah, your uncertainty is bigger. And if your sample is really large, this is in the numerator, numerator, then you know, this value will become smaller. So your uncertainty is smaller if you have larger sample sizes. Now, this is what the standard error tells us. Basically, how uncertain are we about these results? Now, that brings us to how strong is your evidence. How strong is your evidence is t, right? And t is equal to the difference in means divided by this measure of uncertainty. So the greater our uncertainty, the weaker our evidence, and the smaller the difference in means, the weaker our evidence. The bigger the difference in means, the better our evidence, and the smaller the uncertainty, also the better our evidence. Yeah, it's just a division of two things. Okay, how do you then calculate the variance? This is one of the few formulas that I do think you should know by heart. The variance, the unbiased estimate of it, is the squared differences from the mean. You sum them and you divide by n minus 1. Well, you divide by n minus 1 because we don't know the actual mean. We only have an estimate. So we already used 1 degree of freedom in this calculation to calculate the mean, and now we're using the same data again to calculate the variance. So that is one way to think about it intuitively, that you should subtract 1 from your sample size for giving a penalty because you're already using an estimate in this calculation. So we can do that. We can calculate all the squared difference, so 1.8 minus 1.85, 1.79 minus 1.85, etc. And then we divide by 6 minus 1 because we had 6 people in the group, and we already used 1 degree of freedom to calculate the mean. And then you have your variance. Now the problem with variance is, if we are looking at the height, it's in meters, right? But when we square the differences, then you also square the units. So now you can say, okay, men are on average 1.8 meters, and they vary by 0.06 square meters. You know, what does that mean? How do you interpret that? So much easier way to do it is to take the square root again, which gives you the standard deviation, because this is again in meters. So you can very simply say men differ by about 8 centimeter is one standard deviation. So you expect men to differ by about 2 standard deviations in both directions. So about 16 centimeters from their mean is where you expect 95% of males. That's what this value tells you. Now then we have S, and then we just divide by the square root of the sample size to get the standard error. And then we have our measure of uncertainty. So now we have both the difference in means and the measure of uncertainty. We can divide them by each other, and we get the actual t-value. But it's still not quite clear, you know, what, okay, 1.5, is that a lot? Is that a little? Is this a significant difference or not? So that's what I want to show in this lecture, and also in the lecture of tomorrow. I want to show, you know, what does it mean when you calculate a test statistic? So this is what it means. In the t-test, we assume that the t-value comes from a t-distribution. So that means that if I would draw infinitely many samples from the population, then they would all have slightly different values, right? Because they're samples. And they would follow a probability distribution. Now, that probability distribution looks like this if the null hypothesis is true. So if the null hypothesis is true, of course we expect a difference of 0, but we realize these are just samples, so of course they will differ to some extent, but you know, the further away, the less likely it is to observe that large a t-value if the actual difference were 0. Now, what does the t-value then tell us? It tells us if you know, we fill in this 1.585, which is what we observed in our t-test, then we can color in this area, so we can, you know, calculate what is the probability from this value onwards, and that gives you the value 8.7%. So it means if the null hypothesis were true, so you know, if in the population men have a height of 1.8 meters exactly on average, then there's still an 8.7% chance that when you draw a sample that it would have this large a deviation from it, right? Because our sample was 1.85 on average. Is that reasonable? Yeah, if you do 0.05 as your alpha value, then that is reasonable because 8.7% is larger. So you would not reject the null hypothesis and say these men may as well have come from a distribution with a mean of 1.8. Okay, the actual way to calculate this 8.7% from this value is done by integration, right? Because that's how you calculate surface areas. The integral of the t-distribution is not very friendly to solving analytically. I don't recommend trying it unless you have too much time or something, or you want to become a mathematician. But you know, in R it's very simple, so we just ask R. Okay, what else did I want to say about this? Oh yeah, of course, that your sample always differs to some extent. So yeah, you can always expect a t-value that isn't exactly 0 because it's just a sample. Yeah? Oh yeah, sorry. Last thing I wanted to say. So if the null hypothesis were true and you draw a sample from the population, what this probability distribution shows is it shows you how likely is it for a t-value as far away from 0 as the one you observed. And when that value is small enough, we reject the null hypothesis. Okay, that brings us finally to the p-value. So yeah, in this case it is yeah, greater than alpha. If we say alpha 0.05, and yeah, then we say okay, the chance that this is a false positive is unacceptably large, so we don't reject the null hypothesis. Now, some people ask during the other courses, like, why can't you choose alpha after you see your p-value, right? I could see this and say, well, it's not significant at 0.05, but it is significant at 0.1, right? Because it's less than 0.1. But the problem is that your p-value is, again, it's just a measure, you know, it's just a measure of a sample. So it's just a random value. And if you draw a new sample, you get a new random value. So the problem with choosing alpha afterwards is I could also set alpha to 0.8694, right? And say, yeah, it's significant at an alpha of 0.8694. But then you're cheating because you're pretending that this is a theoretical value and not just an estimate from a sample. So it's much better to choose beforehand and just use alpha only as a decision boundary. Is it significant? Yes or no? So in this case, if I had chosen 0.05 beforehand, the answer is no, it's not significant. Okay, let's have a look at another couple of t-values just to see what that looks like. So we're still doing the one sample, one-sided t-test. Are men larger than 1.8 meters? Now, if we had a t-value of 3, then you know we're much further away from 0. So the chance of observing this large a t-value or larger, that is quite small. That's only 1.5% if I color in the area. So in that case, with the same alpha, we would reject the null hypothesis. Now, you can also ask the question, what if the t-value were -3? Does anyone know the answer, what the p-value would be in that case? 1.5. Any other ideas? It's the same test because we're asking, are men larger than 1.8 meters? And we're going to color in this area from -3. Yes? Yes, very good. It's 98.5 because I colored in from -3 onwards, right? If I ask, are men taller than 1.8 meters? and I see that, the t-value is -3, then there is a 98.5% chance that you would calculate a t-value that is -3 or -2 or -1 or 0 or any value larger, right? So it encapsulates most of the distribution. So in this case, you would, of course, not reject the null hypothesis because it is a very normal result under the null hypothesis. Okay, next question then. If the t-value would be exactly 0, then what would the p-value be? What did you say? 50%, he says. That's correct. Because the t-distribution is symmetric, so if you cut it in half, you have 50%. So, yeah, the intuitive way to interpret this is what is the chance of a positive difference from the null hypothesis? Yeah, so if you expect the difference to be 0, then the chance of a positive difference should be equal to the chance of a negative difference if your distribution is indeed symmetric, so it gives you 50%. Then the last question, how large should t be to get a p-value of exactly 0? So 0% chance to get a result this extreme. Yeah? Yeah, I can see why you would think that, makes sense. But here's the thing, I can only plot with a certain resolution. But if I would zoom in on 4, there is still, there's still a little bit of probability left. And if I zoom in on 10, yeah, okay, chance is extremely small, but it's not 0. Same thing for 20, same thing for 100, same thing for a billion, same thing for Google. It's a continuous distribution, it goes on forever. So your t-value would have to be infinite to get a p-value of 0. Yeah, or it would have to be minus infinite if the alternative were less. Okay, that of course never happens because in order for a t-value to be infinite, you would have to observe an infinitely large difference, or you would have to have a standard error of 0. Now, both of those don't happen, but still, your software will sometimes say that the p-value is 0. So I just want to warn you that when you see that, it means that it is too small to print, right? It could be that it just shows 3 decimals. It could be that it's smaller than the machine precision. So I'll quickly show that. R, it's just a computer program. It does not calculate with infinite precision. So you can do dot, let's see, machine. Yeah, dot machine double epsilon. This is the precision with which continuous numbers are calculated. So it's 2.2 times 10 to the power of minus 16. What does that mean? It means that if in any of your calculations there is a value that is smaller than 0.00016 zeros and then a 2, or 15 zeros and a 2, and then R would say, okay, it's 0. It does not calculate beyond that precision because of course you could do that, but then every calculation would cost more memory and more computing power. So yeah, normally you don't have to change this value. You should just be aware that software can in fact tell you that the p-value is 0, but that doesn't make any sense. It just means that it's smaller than whatever it is able to print. Okay, that was the one-sided test and what it looks like. Now let's look at what a two-sided test looks like. So yeah, here's a fictional example. Let's say that that there's no corona times going on here. We're doing everything by the rules, and there are 100 students over here. And let's say that we want to know, does their body temperature differ on average from 37 degrees Celsius? Maybe I assume that some of you here are experiencing fever from the vaccine, or are infected, or have a flu, whatever, and I want to know. So this is one way to do it. Just measure everyone's body temperature and see, does the mean differ significantly from 37 degrees Celsius? In a two-sided test, I would not just be interested in increases in body temperature, but also in decreases. So, maybe this lecture is really exciting and everybody has a high body temperature. Maybe it is really boring and we're all more towards 36 degrees. I don't know. But that's what a two-sided test means. It means we're assessing both kinds of differences, positive and negative. Now, this is what it looks like. In this example, with these data, I'm not going to show 100 data points, but you'll have to believe me. You'll get a t-value of minus 0.8. Yeah, so that means that the actual mean was slightly lower than 37 degrees, but this t-value is very small. And we were testing two-sided. So that means that we have to calculate both the surface area from minus 0.8 onwards in this direction and the opposite, so from 0.8 onwards, because what we're really asking is what is the chance of getting this extreme result in either direction. Well, the T distribution is symmetric, so that means that both these sides give you the same amount of surface area, and in this case the result of the test says if the null hypothesis were true, that on average the students have a body temperature of 37 degrees Celsius, then there is a 40.6% chance that a sample drawn from this distribution would have this large a deviation from zero in either direction. Well, that chance is really large, so with any sensible level of alpha, you would not reject the null hypothesis and just conclude that, yeah, these students may have well have come from a distribution with an average body temperature of 37 degrees Celsius. Okay, are there any questions so far? Okay, then we get to the two-sample test, because this was still all just a one-sample t-test. Now, two-sample t-test, it all looks the same. T-distribution looks the same, calculating surface area looks the same, one-sided or two-sided looks the same. Only difference is the standard error. That one gets a little bit tricky. So yeah, now we don't have one mean, but we have one mean minus another mean. They're both estimated, so it works a little bit different. Now, this is what a two-sided t-test, what the null hypothesis looks like. Either the means are equal or they're not. Yeah, it could be less, could be more. So you could ask both sides of both types of questions with two-sample t-test. The one-sided one, like are men taller than women, or a two-sided one, like does smoking affect blood pressure, yes or no. And in that case, you don't specify beforehand that it should be greater or less. Okay, so here's an example, the same one as the first lecture. We have 10 individuals, 5 male, 5 female, and of course they have a different mean because it's a sample, right? And all samples of continuous variables always differ to some extent from each other. But what we want to know is, do they differ significantly? Because we're not interested in these 10 individuals, but actually in the population they came from. Now, the means is not so difficult to calculate. The standard error, how you calculate it, depends on which t-test you chose. So now we're going to look at what actually happens when you choose different arguments of the t-test in R. So, in case of equal variance, just a small recap, we are assuming that the distributions these people came from have the same width, so to speak, right? They vary to the same extent. In case of unequal variance, I say that, oh, okay, they have a difference in means, but also the extent to which they differ from their mean could be different. Yeah, and again, that is the safer assumption if you're not sure. Okay, what does it then look like? The calculation of the standard error. For equal variance, it is simple. You just have both of the group variances and you divide them by their respective sample sizes, and then you add them. And then you take the standard error of that, and for the standard, you take the square root of that to get the standard deviation, and finally you multiply again by the square root of the sum of both their sample sizes, so that if the sample sizes are not equal, that this calculation is still correct. For unequal variance, it's a bit more involved. You have to calculate both variances and divide them by the respective sample size. That means that we are using more than two estimates. We're not just using two means, but we are also using the estimate of their variance. And we call this a Welch t-test. I've colored this in gray because I just want to show how it works, but you don't have to remember this. There will be no questions about this on the exam. But I do want to show what it looks like, also because it explains, why you would see certain outputs. Because in this equal variance t-test, we assume the variance to be equal, so there's no estimation of the variance involved. So the only thing we use is two means, and then the degrees of freedom is simply your sample size minus 2, right? And we saw that in the previous lecture. We saw that we get a nice integer degrees of freedom, 10. But with an unequal variance t-test, the question of how many degrees of freedom did we use, that's a bit more difficult to answer. It's called Satterthwaite's approximation, and you're not going to do it this year, but if you do mixed models in the next year, it is a very useful approximation to degrees of freedom. But yeah, if we're doing a bunch of squaring and division and subtracting things, this is not necessarily an integer. In fact, it is almost always not an integer. So whenever you see a fractional degrees of freedom, so whenever it has a decimal number behind it, this still means we have two samples, right? 9.537. Okay, used a little bit more than 2 degrees of freedom, so there were 10 samples, 10 plus 2. But, we used slightly more than 2 degrees of freedom for the calculation, so we only have 9.55 something degrees of freedom left. This is why the unequal variance t-test is the safer assumption, because this will give you a t-distribution with a slightly less number of degrees of freedom. Yeah, and that means that it has wider tails, that means that your p-value will be bigger, and that means that you're less likely to conclude a significant difference, which is the safer option, because you're less likely to commit a false positive. Should we test the data on normality before we do a t-test? Okay, I explained this before I started this lecture. Maybe some people weren't tuned in yet, so I'll show it one more time. I've written about this in paragraph 6.3 of Introduction to Biostatistics. I don't recommend testing for normality because it's, in general, I don't recommend testing any of your assumptions for models. The problem is the t-test has a chance of false positive, right? I can devise a test for normality, but that test too has a chance of a false positive. We can also try and make some sort of test whether our data are independent or not. That test also has a chance of false positive. So you're going to conduct more than one test, and all of those tests are going to have a chance of a false positive. And then at the end of your experiment, the total chance that some of your decisions are wrong is going to be much, much larger. So if you have reason to believe that your data are not normally distributed, just use a Wilcoxon test. It's still reasonably powerful, so it's fine. But if you're really not sure, of course you can test for normality with the Shapiro-Wilks test. So Shapiro.test in R. Yeah, and then you enter whatever numbers you want to test for normality. A slightly better way to look at normality is through a QQ plot. So in a QQ plot, we have a straight line here that represents the values you would expect under a theoretical normal distribution. So this is an exact normal distribution with infinitely many samples, would follow this blue line. Now I'm using the one from the package CAR, that's QQ plot with a capital P, because it's nice, it gives you a confidence interval as well. Now the confidence interval tells you I would expect 95% of the values to fall within this range. And then you can check, okay, does my data exceed this confidence interval, yes or no? These data, there's a deviation here, there's a deviation here, there's a deviation here. So you could say, okay, yeah, not normally distributed, have to use a Wilcoxon test. But this is the iris data, and in the iris data set, values only have one decimal number. So we have 1 centimeter large plant or 1.1 or 1.2. But their ruler was no more precise than that. So that's why you see this staircase pattern. That's just millimeters because they didn't measure anything in between. And you can kind of imagine that if these values would be continuous instead of rounded, then it would probably fall within the confidence interval. So testing for distributional assumptions is often more troublesome than that it is going to solve any issues. One thing I do want to say about QQ plots is that extreme values are really hard to assess how likely they should occur because they're extreme values. So this I would definitely ignore. If you see one deviation in the tail, that doesn't mean anything. But in the center, we usually attribute more importance to that. So if you would see deviation over here or over here, okay, yeah, that's not normal. Yeah?
The question about if you want to test for distributions, is there not a correction to solve the false positive relation?
Yeah, of course. And we will talk about correcting for the chance of false positive in the lecture of tomorrow, I think, multiple testing correction lecture. The problem is when you do multiple testing correction, of course your power goes down because you're going to be more strict about what counts as significant, so you're going to lose power. So it's a trade-off. Of course you can do it, but you're going to make more false negatives. So the way to avoid the most false negatives and the most false positives is to, from a theoretical point of view, substantiate your choice for a test or model. Don't test for distributional assumptions. and then just look at only that p-value, and it will have the lowest chance of a false positive and a false negative. Yeah? Okay, so again, this one you should know. It's not very difficult. Degrees of freedom of equal variance t-test is the sample size -2 because you calculate two means. This one you don't have to know. I just wanted to show it because hopefully that clears up some confusion when you see a non-integer degrees of freedom. It just means that this test was performed with unequal variance. Okay, then what do independent and paired data look like? Well, we could plot both data in the same way. So here we have male and female heights, and we see, okay, they overlap a bit, but the important thing to note here is that these men are not somehow paired to these women. They're distinct experimental units, so we have in fact 12 samples, but in this case, if you would measure the same people before and after, you do have 12 measurements, but they are not 12 true replicates. You only have 6 true replicates because the other 6 are a duplicate of the same of the same individuals. When this is the case, just use a paired version of your test. Okay, but here I'm going to show a little trick. This is in Rdpair T-Test, right? This is the only one you should remember. But there's another way to do pair T-test. Here I calculate the difference, which is before minus after, and then I specify that the null hypothesis should be that the mean is 0, and I just do a one sample T-test. And well, we can do find the differences, but I will just spoil it now. There are no differences between these two tests because a pair T-test is just a one sample T-test for the differences in groups. Yeah, so that's what happens under the hood. Again, not something you have to remember per se, but yeah, it can help to know what's actually going on. Okay, then the non-parametric alternatives. I will explain how these work. There are no questions about this on the exam. I just want to show what they do to hopefully give you some intuition as to why we use this test and what it really says. Okay, so again, short recap. Conditional normality is not always a reasonable assumption. Maybe your distribution is really asymmetric, maybe it's discrete, or maybe you already know that it comes from a different distribution. In that case, you can use the non-parametric alternatives. Okay, but before we go to that, let's talk about when normality is a reasonable assumption. And that has to do with the central limit theorem. And that states that when you sum a large number of independent effects, it will follow a normal distribution. It's not a very specific recapitulation of the central limit theorem, but a more specific one is that when you keep drawing samples from a population and you calculate their means of those samples, then those sample means will follow a normal distribution. That might sound a bit convoluted, but what it means in practice is that it does not matter what these individual effects are that affect the process. As long as there's a large sum of independent things affecting a continuous outcome, then summing it will yield a normal distribution. So, for example, when we look at human height, it's affected by around 700 genes that we know of, probably more, as well as, of course, many environmental effects, and even whether you just stood up or whether you just got up, I meant, or whether you have slept for 12 hours or whether you did really heavy squats, probably affects your height at that moment. So it is affected by a really large sum of independent effects, and the cool thing is it doesn't matter how these individual things affect it. The sum of it will probably yield an approximate normal distribution. Now, of course, the more independent effects affect something, the more it will resemble normal distribution. Because we know that it's affected by so many things, it is reasonable to assume that given a certain category, so we only restrict ourselves to male adults in the Netherlands, then it is reasonable to assume that that should follow a normal distribution, at least approximately. Okay, but when it doesn't, you can use the non-parametric alternatives. So this is called the Wilcoxon rank sum test, also known as the Mann-Whitney U test. It's the same thing, just it was discovered by multiple people around the same time. It tries to answer the question how likely it is that a randomly chosen member from one group is greater, in whatever value you're measuring, than a randomly chosen person from the other group. So on average, you know, what is the chance that a person from group A is greater than a person from group B? Now, the way that works is by calculating the ranks. That's quite simple. Here we have a table. These are the same individuals I showed earlier. So we have 6 males, 6 females, and they all have a different height. I can just rank these observations, you know, lowest to highest. And then we say, okay, this observation is the lowest of all of them, so I give it rank 1. This one is the second lowest, so it gets rank 2, etc. Yeah, and this is the tallest male in the entire sample, so this one gets rank 12, the last one. Now, the only thing to note here is, of course, what if 2 people have the same height? Or, you know, of course, if you keep measuring with infinite precision, they probably don't have the same height, but you know, rounding errors can occur, so ties are possible. When that happens, just give them rank 6 and 7, for example, and an average. So they would both get rank 6.5. Okay, so we do that, and now we have the sum of ranks for the males, and we have the sum of ranks for the females. So we can calculate 2 scores. You can calculate the score of men, which is 55, and we can calculate the score of women by adding all their ranks, which is 22.5. Now, then there's, depending on the software you use, there's different ways that this Wilcoxon statistic can be calculated, but they mean the same thing. It's just from a different perspective. Is it group 1 or group 2? So this is the way, let me quickly cheat by looking over here. Oh yeah, this is the way that R does it. The first one, it uses the score of whatever group you specified first. So if you do a t-test, men, women, it will calculate the Wilcoxon test statistic for the men, because that's the first one you entered. So we take the score, yeah, this one, and we do something with the sample size to correct for that, and then you get your Wilcoxon test statistic, in this case 34.5. Of course, you could do it also for the other group and you get different value, but it doesn't matter in the end. Then, using this and a Wilcoxon distribution, which I'm not going to show here, but it works the same way. Just look at the surface area from then onwards, and you'll get a p-value. And indeed, we'll see that entering these data in R, height M, height F, it will give us the Wilcoxon score for the men. So indeed, we see W equals 34.5. But if I had said height female, height men, then female are the first group, so this value is what we would expect, and indeed that's what we see over here, 1.5. But under the hood, it is still using both of them in the calculation of the p-value, so it will give you identical result. Doesn't matter how you specify your t-test. Yeah, so again, you don't have to remember this, it's just to give some intuition. What you're really doing is just comparing the ranks. Yeah. And again, the calculation of p-value is a bit involved, but if you want to know, R uses a normal approximation, you can look it up. Then we have the paired version. The only difference in the paired version of the Wilcoxon test is that we need one more piece of information. We have the rank, but we also want the sign, because we have positive and negative differences, and it's basically looking for symmetry. Are there as many positive differences as there are negative differences? And if there is no such symmetry, then apparently the difference is not 0. So you just add all the positive ranks, and you add all the negative ranks, and now, okay, we call it V because W was already taken. And again, we have this value. We use it in some way that I'm not going to explain, that calculates p-value. Yeah, again, here we see V equals 20, so that's exactly what we saw over here. And you get a p-value. Not this again. Okay, yeah, good. Yeah, so just to be absolutely clear to everyone, the second part of this lecture is really just meant to provide some intuition into how things work and to show that it's not super complicated, it's just a couple of additions and divisions. But you don't have to know this for the exam. There will be no questions on how the t-test actually works. Okay, so yeah, that is all for today. I will show the exercises one more time. So yeah, the exercises are on chapter 5. I updated it this morning, so if you already saw it earlier, please have a look again. There are some exercises here under the choose the right t-test, and there are some exercises here, which is interpretation of the output. This is of course useful because eventually we're learning all this so that we can actually use it. And this is much like what you can expect on the exam, that maybe we omit a value and you have to calculate it, or maybe you see the output and the question is asked, like, is this significant, or what was the standard error, stuff like that. So if you're able to answer these up to 5, then you're more than prepared for the exam with regards to the t-test. There are also some harder exercises, so yeah, you can in principle calculate a lot more from these values, but yeah, I don't want to make it too complex because it's not a math class, but you can do it. So that's question 6. Then there's question 7, which is just choose the right t-test, but the choice is a bit more difficult. So we look at some more interesting examples, like for example in clinical science, it's common to do what is called a non-inferiority design, where you look, is my new medicine, is it not worse than the existing medicine? If the answer is yes, it gets approval. Yeah, you can do it with a t-test. So yeah, if you want some challenge, you can look at that. If you just want some practice, look at the questions 1 to 5 of both, 1 to 3 of choosing right t-test, and 1 to 5 of interpreting the output. Yeah, that is all for today. Tomorrow, I think we're going to talk about multiple testing. Let me check. Yeah, tomorrow tomorrow in the morning you have some extra time for the t-test. I will upload some extra assignments in case people are already done. So we start with the lecture at 10:15 tomorrow, and then we're going to talk about multiple testing. Are there any questions still? Yeah, so tomorrow I will be here from the morning, so you can work on the assignments and ask questions if you want, but the lecture starts at 10:15 tomorrow. It's also in the schedule.
Will there be new assignments for tomorrow morning?
If there are people who are already done with everything, I will make some extra ones, yeah. But in principle, it's just these.
Ja. Dit is binnen een kwartier gedaan. Als je 6 leest, dat is de moeilijke. 6 is gewoon, je kan gewoon in Impaired gewoon SD zetten en dan gewoon x aangeven en dan bedenkt hij daar de standaard differentiatie van.
Ja, dan moet je wel x hebben.
Ja.
Als je alleen de output hebt, dan gaat dat niet.
Oh ja. Anders was het inderdaad wel heel makkelijk geweest.
Okay, I see no more questions in the chat either, so I will end the stream. If you do have questions still, you can ask them on Brightspace.